Welcome to part 3 of Decision Analysis for Agricultural Development. I'm Cory Whitney. In this section, we're going to talk about model building. If you haven't already watched the first few sessions, maybe go back and have a look at those. They should be here in the same channel where you found this video. Now we're going to speak more practically about how these models are applied and how we go about building and applying these. So thanks for tuning in, and I hope you enjoy. This is part 3 of a 6-part mini-series on decision analysis. Part 3, model building. So in order to build models, we follow a few modeling principles, and those include incorporating all the important aspects into models. So as you practiced in the last video, you thought about what are some important variables and that have a lot of uncertainty. We need to make sure that these are all incorporated into the models. We use all sources of information. That includes local and expert knowledge, maybe most importantly. And we explicitly consider uncertainties about inputs, processes, and outputs. So we may go from something like this, a very complex, hopefully extremely complex model that incorporates all the important factors, but maybe in the first case doesn't really have clear and mathematically modelable relationships, maybe lots of question marks, arrows going in both directions. Ultimately, what we want is something called a directed acyclic graph that is ideally, very ideally here, clear indications of which factors influence which other factors and how these relationships work. Here in this simple example, I show red and green so that you can think about this as A has a positive effect on A3 and a negative effect on A2 and A1, for example. But ultimately, there's a clear outcome of interest. In this case, let's say it's B4. We'd like to know what influence A has on B4. So we follow this mathematically. We run it with uncertainty distributions many, many times so that we can identify the best, based on all of our uncertainty, the best outcomes. We examine the alternatives in an explicit and logical way and use a single coherent scale. It may vary as we do that, and sensitivity analyses to look for changes that can influence these decisions. We identify key uncertainties for measurement using something called the value of information analysis, which we'll talk about in detail a bit later. And we update and clarify the model whenever new information becomes available. As long as the project is still active and we still have the model running, we can always update. So what we do in order to build these models is that we convene experts, stakeholders, and decision makers to jointly develop a causal decision model. Here we are in Uganda on the left and in Kenya on the right, dealing with two models, which we will discuss in detail a bit later. But we bring all the experts together and try to facilitate a process whereby they generate a decision model. We gather all the subject matter expert knowledge. And expert in this case doesn't just mean university professors and academics. It means really people who know about the situation. And if we're talking about smallholder farmers, that means that smallholder farmers should be at the table helping to assess the decision and the impacts, the potential impacts of the decision. So context and decision-specific information gets put into this conceptual model. So essentially what we do is we bring those experts and analysts, that is our team, really, people who are experienced somewhat with generating these kinds of models, and we together go through the process of framing the decision. What is the decision? What are the important factors that influence the decision? How does it work? We analyze that decision, that is, we go through and we really think critically about the various relationships. Are they sensible? Which direction do they go? How do these relationships work? And then ultimately we build a model out of this. Really analysts and experts together, an iterative process whereby they can give each other feedback and we can make sure we have something that makes sense. It's kind of a peer review process. I've framed this in these 4 phases. I call it effort. Of course, as we keep saying, it's really important that we define a specific problem, a real decision that needs to be made, resources that are allocated with a specific outcome in mind, and uncertainty about what that outcome might be. So we go through the process of divergence, that is everybody sitting together, collecting ideas, having an open discussion, gathering lots of variables and unpacking and disaggregating complexity, trying to come up with that more complex model structure. Next, we do a process of convergence where we clarify the relationships and the concepts. We have a focused discussion. We develop concrete descriptions, that is in the form of circles and arrows, to build one of these, what we call a directed acyclic graph, a DAG. And we do a peer review of that graphical model. So we make sure everybody has a chance to give feedback. This can take long time, but it is worthwhile to get a really logical structure that makes sense to everyone. Finally, in this final stage, which I call emergence, we program that model as a mathematical formula. We identify the important variables that are in this model, and we follow up and share, and ultimately give some decision support. We say, this is what we've learned, and here's what we have in terms of uncertainty, but ultimately, this is the decision that we think would make the most sense. So this is a collaborative process, and we do this mostly in workshops. Of course, in these times of Corona, it changes a little bit, and some things are being done remotely. But essentially, functionally, we mainly get together with experts. We work together with the analysts and the experts. We build a model and create these forecasts. In this case, it's working in Kenya on the problem of fruit trees. So there are different ways that we can work with groups. We can work in plenary, that is with one person speaking at a time and everyone listening. We can work as on an individual level, that is one person thinking by themselves. Or we can work in groups, which is great, right? So I try to build a balance of all of these interactions between these different stages, that is, use some time in plenary to define the scope and make sure that we have a clear decision in mind and everyone agrees. We can break that down in plenary, break that decision down into specific subsections, that is, smaller questions. And then we can divide people among working groups. And each of these questions, these sub-questions that we've built out of this decision, we divide working groups among those questions. Everyone is asked to consider the question on their own, and then they can consider that question with their neighbor and share insights from that discussion with their small working groups and create a graphical representation of these ideas. And we repeat this in a World Cafe style session. We repeat this for every question until ultimately we've got a final graphical model. We combine all of these graphical models together once we've had these discussions around the room. To generate the mathematical model, we often use the R programming language. And if you've taken the R course, or if you're planning to take the R course, then we'll talk more about that in the future. But we use the R program, or we use other networking programs like a gainer risk. Norman Fenton, who we talked about earlier, is the main developer for a gainer risk. And that's also a really useful tool for building Bayesian networks. Here we are with one of our colleagues in Uganda, where we're taking those graphical representations that people drew, that's on the wall there, you see them hanging on the wall, and we're trying to then plug those into the gainer risk program to build a Bayesian network. And essentially, what we need to do is define, based on these circles and arrows that people have drawn and the stories that they've told us about how these work, we have to define conditional probability tables. Behind every variable, there's our understanding of how that influence works, how those variables interact. This is an example. You don't need to see that in detail, but this is an example of one part of a model that we did in Kenya, representing the influence of introducing fruit trees onto farms and how that will ultimately affect the zinc gap, that is how much zinc people are lacking in their diets, and whether this will have a measurable or whether it will have an effective influence on whether or not people are getting enough zinc. In the R programming environment, this is a very simple example of running the Monte Carlo MC simulation function in R in the decision support package that's managed by our team and initially generated by my boss, Ike Ludeling. And you can see more about that if you want from these repositories that I told you about earlier in the GitHub folder. What I'd like you to do now is to think of a decision, agricultural development decision, and take some time to draw that decision as a conceptual diagram. That is, to take some time to think about a development decision, agricultural decision, something related to your research, and draw a picture of it. You can use any number of tools. I'll share a few in the Slack, options for drawing conceptual diagrams, but feel free to do that in PowerPoint or whichever tool you feel most comfortable, and share that with us, please, in the Slack. Looking forward to seeing what you come up with.